So in some sense, value iteration, the message is being passed from the high and low value, obviously high and low value states to all the, normal states. Most life is just normal states, right? And in fact, if you remember even from the search algorithms for A-star search, the worst case happened, if you did local search in particular, you know that for the local search, the worst cases happen when you have just, basically a plateau. Okay, so it's not very clear if you're standing in the middle of the Deccan Plateau of India, which direction is Everest, just by looking at the local topography. You get up to the Himalayan foothills, maybe you will say, well, this seems to increase my height, so I'll take this. And you will get stuck anyway in a different reason because you have local hills. But at least you have some direction there. In plateaus, you don't know where to go. And this guy is essentially, if you do enough value function iterations, everybody realizes their inherent value. And I cannot overstate the importance of realizing that the value of a state is with respect to the optimal policy you are supposed to follow. So don't ever complain that why did you say this state is so darn good? If somebody said it's good and you didn't feel it that way, it's assuming everything else is the same, the dynamics are the same, the reward function is the same, it's because you did not compute the optimal policy yet. Okay, and if you run the value iteration for k iterations, it's like looking k steps ahead before deciding what the policy is. Okay, and the effective number of steps you have to look at to get the optimal policy seems to depend on the steepness of the discount. If the future matters too much, then you need to look a lot ahead to see what's the right thing to do. If the future doesn't matter that much, then you don't have to look that far ahead. And the number of iterations of the value iteration are essentially how far into future you are looking. At the thinking time. Not at the action time, but at the thinking time. All of this is thinking. Okay? So anyway, then for any given value function, there is a greedy policy. Okay, and when your value function is the optimal value function, then the greedy policy with respect to that value function is also the optimal policy. And it's called greedy because each state is deciding the best action to do just greedily based on the values of its neighbors, nothing else. It's not thinking any further, it's just using the value functions of the neighbors. And if one particular action has expected value little higher than another action, you say this is better than that, greedy. That's why. And the greedy selection winds up being the optimal thing if in fact the value function underlying is also optimal. Okay? Okay, the last thing I want to do today, we haven't yet gone to the policy iteration, but today but by the way, one good thing is value functions, value iteration is really the fundamental algorithm for MDPs. If you get a new type of MDP, you first try a value iteration algorithm for it. Because it turns out, and as I answered to one of the questions that came up, and we'll talk about it again later, policy iteration is not guaranteed to converge for a large class, for many classes of MDPs. Value iteration is guaranteed to converge more often. Okay? So, and this for the infinite, when I say more often versus less often, I mean for classes of MDPs. For the particular class of MDP we are considering here, which is infinite horizon discount with discounted MDP, where discount factor is less than 1, it's guaranteed to converge. Both value and policy functions are guaranteed to converge. Okay? So here are some ways you can improve the speed of the value iteration. Okay, basically the number of iterations you take. Okay, it turns out that actually there is no obvious way of bounding the number of iterations that are needed because it's a real valued function, and you need to put an epsilon, and with respect to epsilon, you can put some loose bounds as to how many iterations you might need, but those are typically quite high. Okay, but you can improve the speed of value iteration without, in two different ways. One, of course, is you can say, I don't care about exact anymore. I won't mind using approximate value function and approximate policy. I won't do that right now. But that's a very reasonable thing to do. Because again, as I mentioned, the difference between a hacker and a CS guy is you know what the optimal is. It's not that you want to use the optimal. For a large enough problem, you probably, it's important to actually live and see another day than to get the badge of optimal action. Okay, but if I keep the optimal policy, I can still do the algorithm faster. That means I can make it converge faster by using all sorts of interesting ideas. One idea is I started by initializing the value function. Basically, value iteration works with any initialization, right? In fact, the default initialization that people use is to initialize the value function to be R of S. In the example, actually, they initialize it to zeros, and then in the first iteration, it becomes R of S, which is the reward of the state. Okay, so at least you will reduce by one iteration if you initialize by R of S. But suppose you initialize by V star of S, then how many iterations would you need? You have a very rich uncle who just happened to tell you, this is V star of S, you put V star of S, and you're done. You may not have that rich an uncle, but neither are you so impoverished that the best you can do is R of S. Many a time, you might have a reasonable idea of what is the value of various states. Okay, in particular, suppose you were to think, again I'm asking for your intuitions right now, suppose you were to think that this plus 10 is somehow the goal state. And these are sort of bad states you don't want to get in. You're trying to find, your policy is trying to get you to the goal state with the least number of actions. Okay, if you acted as if everything was deterministic, if the actions were deterministic, right? That means I relaxed the problem and removed the uncertainty. I just made it deterministic, let's say. Then I'll get the shortest path. I can find single destination, shortest path from every node. That is the heuristic. Okay, the path basically, the shorter the path, the higher the reward. If you compute sort of approximate shortest path from these guys, okay, and then you put basically the value function to be those numbers. If you do that, the number of iterations will reduce. Okay, since it's guaranteed to terminate no matter what your initial value function is, it's also guaranteed to terminate if you do a, sort of a close to reasonable heuristic. I'm not talking about things like admissibility. For those of you who are from A-star search, who know A-star search, in fact, a reasonable question is, can I get any additional properties if I were to, initialize every state with H of S, where H is a admissible heuristic. By the way, in saying so, I also combined your two words, A-star search and MDP. In A-star search, it looked as if all you care about is the place you're starting from, the place you're going to, and only the states that fall on the way. And you don't need to know what to do in other states. That's because you'll never get into those other states. Right? But for a heuristic, for A-star search, is the heuristic supposed to be determined only for a couple of states, for all the states in the problem? All the states. Why? During thinking, you need to consider being in any possible state. So H of S is sort of actually like V of S. In fact, H star of S, which is the perfect heuristic, is well connected to V star of S. If you have a deterministic MDP, that means you have actions that are deterministic, and you have a goal state, you can write it as an MDP still. Okay? And it's kind of unnecessarily, breaking an egg with a sledgehammer. But yet you can still do it. If you do that, and if you compute the V star of S, that would be your H star of S for that problem. That's the connection between A star search and MDPs. Okay? So for our problem, all I want to mention is, first of all, you can start with a better initialization of the heuristics. That will improve the speed of value iteration. And the second idea is, I made this picture has actually acted as if everybody changes their values synchronously. right? Everybody, so V of 0, everybody changes at V of 1, they use everybody's V of 0 values to reset their values. And then next, V of 2, everybody uses the V of 1 values of their neighbors to reset their V of 2 value. It's all being done synchronously. That's the picture I painted. It turns out, as far as the convergence of this algorithm is concerned, it doesn't have to be asynchronous. I'm sorry, it doesn't have to be synchronous. You can do asynchronous updates. Okay? And what that means is once you allow asynchronous, once you realize that asynchronous value iteration is possible, one obvious idea of asynchronous is if you are already, if your neighbors already, you're in the V2, and your neighbors already got their V2 values, must you still use their V1 values? Do you understand what I'm saying? No reason. At the minimum, you say, well, even within the synchronicity, you just happen to do a little before me. I'll take whatever you currently have, your best value, best estimate you have, and I just use it. A much more interesting idea that asynchronicity allows is you can do what's called prioritized updates. There is no real reason as to why every state is just as interesting as every other state. There are some states that sort of fall on the approximate path from where you are to this happy state. Look the neighborhood around them and update their values more often. The states that are far away from that, you can do it less often. And this is actually connected to a question that was asked on the web, on the forum last class. Okay, if I start with a single line plan, act as if all actions are deterministic and find a single sequential plan, that just gives me the sequence of states that I would get if I was really lucky. And then I'll get to the goal state. Okay, but then I have some more time now. What I can do is I can look around the states that I can get into from this line plan and only consider them more often. So you basically start updating them more. Okay, so in general, you can decide how many, which states to update. You don't have to do it synchronously. You can update some states more often and some states less often. Just one second, okay? And what that also means, and in fact, you might ask, what about the proofs? It turns out that the proofs will all hold as long as everybody gets updated infinitely often. It doesn't matter when their infinity comes. When I joined faculty position, they told me faculty positions are extremely flexible. It doesn't matter when you spend your 80 hours. You can pick the 80 hours yourself. Okay. Similarly, it doesn't matter how your infinite number of updates are going to be scheduled. As long as by the end your infinity also gets done, then you are guaranteed to converge. And since we are going to schedule the updates such that the guys that are more important, the states that are more important are going to be, you can use nice heuristics to decide which states are more important and update those more often so that you will know what to do in those states. The states where you are likely to find yourself in, you update those to get the optimal policy. Okay? One other interesting thing which, it's kind of beyond, this point, but people have done it, is you can actually look to see when a state has stabilized. It's not going to change any further. And that is by labeling. Sync states have stabilized. They're never going to change their value. Okay? Any state, all the neighbors of the sync state, once any of them, if your neighbors have stabilized, then you have stabilized. So the labeling can be done such that whether or not some state has stabilized. And you can essentially, work on those states that haven't yet stabilized. That is allowed because of the prioritized fitting. It's a great idea. And with respect to your connections to authority subs and PageRank, you can do PageRank, PageRank updates, not necessarily synchronously, but update the important people's pages more often. Okay. Yes.
Would it be a very good idea to prioritize states that are neighbors to states which have changed drastically during the last iteration?
That's basically the kind of thing that's exactly the right kind of idea. You consider the residual changes. You keep track of residual changes. So the point is, Now that prioritized sweeping is allowed, I'm actually allowing you more, controls. Now, you might say, why did you give me this control? Before I could just nicely write, a simple algorithm, which probably all of you wrote, which is, just go synchronous, lockstep, one iteration to next iteration. Now that I tell you can do better, then you have to say, how am I going to do better? You have to think about ideas for setting up priorities. And what you said is one reasonable idea. Those are the kinds of ideas that people use. Okay? Now, the interesting thing is when you do these kinds of prioritized sweeping, etc., you can, and if you're going to stop after like 10 minutes and say, I don't feel like doing any more iterations, you're more likely to have, found closer to an optimal policy this way than otherwise. However, eventually, if you haven't found the optimal policy, then I can always ensure that there is somebody else who can do better than you. Okay? And my last analogy for today is Captain Sullenberger. That's the guy's name, right? The guy who landed US Airways flight on Hudson. Okay? If you are a pilot and you're trying to figure out what are your optimal actions, what is the chance that you will figure out what is the optimal action when both my engines have been knocked off by these random birds? And I'm still in a city area, and I have this huge plane, and I just basically need to bring it down without getting a huge negative reward. Okay? Most people who have reasonable policies would not have figured out the optimal policy for that case. And they are still flying our planes right now. And you're okay because most of the time both your engines are not affected by two unruly birds. So they're never checked. But when they get checked, this guy actually, then you found that he has spent more time figuring out his optimal policy, even for states that are so unlikely to occur that any prioritized sweeping would have not even come to that state. You see what I'm saying? That's the theoretical guarantee you'll get if you take the hard way. Sullenberger. Okay? Stop.